Okay, hello everybody. Welcome to this webinar, Interpolation, Turning and Milling with the TNC 640. My name is Michael Wiendl and I want to show you in this webinar how to program the interpolation turning cycles on the TNC 640. First we will do a little presentation to show you the theory, and afterwards we will do a programming example at the programming station. So, the fundamentals of the interpolation turning. So, we program a rotating symmetric contour in the X and Z coordinate system. And then we can choose the variant of the machining. So, if the spindle is coupled or the spindle is not coupled. So, the movement is a 3D spiral movement. So, a movement in X, Y, and Z around the rotary line of the center line of my rotating symmetric contour around an X, Y, and Z. And if you program that the spindle is not coupled, then you can use it for a normal milling tool. If you program that the spindle is coupled, then you can also do it with a turning tool. And during the movement in X, Y, and Z, this spindle is always looking to the middle or away from the middle, depends if you have an outside or inside machining. For this we have two different cycles. The cycle 292 is for interpolation turning with a contour, and the 291 is just for interpolation turning coupling the spindle. This cycle we watch later. We can use the cycle 291 together with an output of a cam system, for example. The cycle 292 needs the cycle 14. In the cycle 14 we define the label where we did the contour description of my interpolation turning contour. Also we need the option 98 for interpolation turning, otherwise we cannot use the cycles. At first we look at cycle 292 because this cycle we can often use directly on the control for programming. So this is a special application example. So we have an rotating symmetric contour and we want to do this contour with a milling tool. So you see the structure of the ANSI program. We call our tool, we make an M3. The next step, we program the cycle 14 with contour label 1. In the label 1, you see the description of the contour in X and Z. And then we program the cycle 292 and we go to the middle of the machining and call the cycle with M99. We find the cycles, it's cycle def, special cycles, interpolation turning, cycle 292. And we can do an inside or an outside machining with this cycle. The contour is important. We need to describe the contour in the X and Z coordinate system. So we program the contour in a subprogram without any radius correction, only the contour description in radius. So there is no possibility to program it in diameter. We need to program it in radius. So we need to be sure that there are no back cuts inside of the contour, that the contour constantly falls or rise, so there's no the direction is not allowed to change. Because of this, we need to define, for the example here on the right side, we need to define one contour for the inside and one contour for the outside. Because both together are not allowed, because when I switch from inside to outside, I will also change the direction from constantly go up to go down, and this is not allowed. And also important, the programming direction is also the machining direction, so there is no possibility in the cycle to change the direction. For this, when we define the contour like this, so from the top position to the down position, then this is also the machining direction. So here we see the contour, so beginning at the top and go down till the end. In X and that without any Y or anything inside, just to do the programming here. So then inside of the cycle, we can decide if we want to work with an active spindle coupling. So for milling, the spindle coupling should be off. So we can use it with a normal milling cutter out of the tool table. If you activate the spindle coupling, yes, then you can use also a milling tool with a coupled spindle. You can also use a turning tool, so a tool which is defined in the tool turn TRN table. So you can use this cycle also on a milling machine. If you have a mill turn machine, you can decide if you want to use a milling or a turning tool defined as a milling tool or a turning tool defined as a turning tool. Both examples are possible. For the end mill, also interesting, the control compensates the R2. So the corner radius of the tool will be automatically compensated. So you can do the same contour like you see with an end mill without any corner radius, with a ball nose cutter where the radius is the same like the R2. And you can do the same machining also with a torrid cutter where the radius, the corner radius is more than 0 but smaller than the radius. And the control will automatically compensate these radius here. Okay, for programming you can decide the parameters, so spindle coupling yes or no. So if you say yes, so 1, then spindle coupling is active, then the spindle is orientated during the movement, always to the middle of the machining. Or if you say 0, then no spindle coupling is active, then you can do it with a milling tool. Also the direction, if it should work clockwise or against the clock. Inside or outside machining. Also the start position, the starting point. So there you describe the first point of the label, of the contour label in X. And also the oversize. So the oversize is for the complete contour, so not oversize in X or in that. It's for the complete contour. For example, when you do it first roughing and afterwards finishing, then you can use this oversize for the operation. Then we have the millimeter per revolution is the infeed. So that's how much way the control should do during one 360 degrees movement. Also the clearance to the side and the clearance height. This is important. The clearance height is always regarding the active datum, the active preset what we have here. And then we go to the middle of the machining and we call the cycle with M99, cycle call POS or cycle call PAT. And then we could do, for example, this application here. So roughing with a diameter 16 end mill without spindle coupling. In the next step, we finish the contour with a turning tool with spindle coupling active to get a turning surface on a milling machine, for example. Also possible to do this in the tilted working plane, so also together with a plane function, we can also use the interpolation turning cycle. We can also combine it with a pattern definition. For example, we have here a pattern with a lot of drillings, and every drilling needs a radius 10 starting. So we can use the interpolation turning for creating a good program here. You see a nice 3D spiral movement. The radius 2 is will be automatically compensated by the control, so we can use this very easily to get a good movement here. So let's take a look at the machine. So interpolation turning with cycle 292 with a milling tool. So we start in the middle, and now we see a nice 3D spiral movement along the workpiece. So the spindle is turning with M3, and we get our contour machined in the workpiece. And the next step, we do the same with an turning tool. So interpolation with a turning tool. So orientation, and then the machine will do a movement, and now it depends on the how fast the machine could handle this. The cutting speed depends on this. So the best is always if you have a contour radius nearly the same like the tool radius, because then for an inside machining, then you can do then you can use nearly the complete spindle speed of the milling spindle to get a good cutting speed here. Of course, for an outside contour, as bigger the diameter is, as slowlier the cutting speed would be. It depends on the machine what we are using here. So, and we can watch this at the programming station. So I prepared a little bit. So I have a program. It's looking like this. So you see, this is my blank. And what I want to do is at first an inside interpolation turning process with a milling tool. And outside I want to do with a turning tool. For this, I already prepared two contours. The label 1 is for the outside machining, and the label 2 is for the inside machining. So we start at first with the inside machining. For this, I make a tool call to the ball mill diameter 6. This is a ball mill cutter with 3 mm radius and 3 mm radius 2. So cycle def, special cycles, interpolation turning. So before we can program the cycle 292, we need the cycle 14. So we can say go to and 14. So contour label 2 we want to use for the inside machining. And cycle def, special cycles, interpolation turning 292. So we don't want to have a spindle coupling, so we say spindle coupling 0. The angle of the spindle, we need the angle of the spindle when we have spindle coupling active and the tool is defined as a milling tool. Then we can use the angle of spindle to correct the angle of my cutting tool here. The change tool direction M3 or 3 or 4 defines clockwise or against the clock. We let it on 3. And then I decide the machining operation. It should be inside +1. And the surface oversize should be 0. In feet, I choose 0.8. And the feed rate. The feed rate is a little bit special because we define the feed rate in millimeter per minute. So it's not a feed rate, it's a cutting speed. And it depends on the machine, but there we can go really high to get a good cutting speed on the surface. Contour start radius. There we need to go down to the contour, and the contour starts at x 9.1. You can see here in line number 40, x 9.1. So contour start radius 9.1. Clearance to the side. For inside machining, I make this really small, just to have enough space inside of the drilling here. So linear x0, y0, and maximum M99. So you can just follow what the machine is doing. So we get a nice radius here. So the model quality I can make very high and restart again. And so we have a nice 3D spiral movement out of the interpolation turning. So, and the same we can do with our outside contour and with the turning tool. So I just select the block and copy block and insert the block, and we just change the parameters what we need. So contour label 1, spindle coupling is active now. The angle of spindle is 0. That depends on the machine. So if the tool is inside and you make spindle orientation to 0 with M19, for example, then the tool should look from X plus to X minus for an outside machining. And that's very important. If the tool is not looking in the X minus direction, then we need the angle of the spindle or the orientation in the tool turntable. Change the tool direction. There we need to take a look at the simulation if the tool cuts in the correct way. Machining operation should be outside. Surface overside 0 and in feed. Okay, feed rate. So we can just go down here and watch label 2, label 1, X12. X12 and 2 millimeters. So now we check if the direction is correct also for the inside. So tool will come. So you see, we need to change it for inside because inside was, make it a little bit slower and we can see it better. You can see the tool is going right the contour, but we want to get a better cutting situation. We want to get it against the contour. So we can change this with the parameter here. Change tool direction. 4 says make it on the other side, in the other direction. So tool will come again. And now you see left of the contour. So now that's what we want to have. So, and the same, we check outside the same, it's right. So there, of course, it depends on the cutting plate. So if the cutting plate is cutting in this direction, this is okay, but if the cutting plate cuts in the other direction, then we need to change it to 4. So first step, and now you can see. So you can change the behavior of the contour with the machining direction. And now we get a nice spiral movement, and the spindle is coupled. So during the machining, the spindle will always follow the linear X, Y, and Z movement, and always looks to the middle of the programmed contour. And with this operation, we get a turning surface on a milling machine. And it's an easy way to program such a rotating symmetric contour. So, back to presentation. Next step, next cycle is the cycle 291. The 291 is only spindle coupling, so not combined with any contour cycle. So this cycle 291 we can use when we have a CAM program. For example, the application here, we have a CAM program, and the CAM output was this contour. There's a back cut here. So the CAM program is a linear X, Y, and Z movement. And we just add the cycle 291 spindle coupling. And when the control gets the information of this cycle, from this point, the spindle is coupled. So during a movement in X, Y, and Z, the tool always looks to the middle of my defined first center and second center. We can program it with cycle 291, and we also need an M99 after programming, otherwise the coupling is not active. So what do we need? We need an NC program. The best would be an NC program with a 3D spiral movement. And we need to switch on the coupling before the machining and switch off after the machining. We can use this if we have a CAM program, or also if we need a back cut, for example. It's important that we cannot do any changes inside of the control now. So the direction, the defined direction is regarding the CAM program, the CAM output, and also if it's clockwise or against the clock, this is regarding the CAM program. We also have the spindle coupling here, and we also have we have here the center of the first axis and the second axis. So there we define the middle point for my coupling. So the tool will always look to this point during the machining. And we have a little bit of special Q parameter, the 561. This parameter is only interesting if you if the tool is defined in the turning tool table, so in the tool turn.trn. Because if you define a tool a tool there, then the control needs to handle the XL value as radius. And because of this, if you activate or if you use a turning tool, you should use this parameter with setting number 1. Otherwise, it could be that the movement is not correct. So, but this parameter is only important if the tool is defined as a turning tool in the tool turn. If it's defined as a milling tool, then you can use it normally without this parameter inside. So before the machining, you need to couple the spindle. So cycle def 291, spindle coupling on, and M99, then it's active. And after the machining, switch off the spindle coupling, so spindle coupling 0 and M99 to activate this cycle. So the cycle looks like this. Interpolation turning with a turning tool and cycle 291. So you see an outside machining. So the control is just following the X, Y, and Z coordinates of the ANSI program, and during this, with cycle 291, the spindle is coupled to the movement and always looks to the middle of the defined, or to the defined center in the first and the second axis. So some tips and tricks for the programming here. The first tip is if you have a DXF file from your contour, like the DXF file here on the right side. So I just have a correct view on my interpolation turning surface, and now I just put the middle in the datum in the middle of this DXF, of this view here, so in the middle of my contour, and then I can select this contour, just what I want to have, and I save it as a program. But now the output is an X and Y, but the Y coordinate I need to replace with Z coordinate. So I have the program here with X and Y coordinate. So I say find, the soft key find, and replace, and then I can say find the text Y and replace it with Z, and replace all, and then I have the program from before in X and Y is now X and Z. So this I can use, for example, for a DXF file. Also a very interesting function together with interpolation turning is the CTC, the crosstalk compensation. Because during the interpolation turning movement, we have a very high feed rate. And the very high feed rate is, of course, a very important thing against the accuracy of the workpiece. And the HEIDENHAIN control offers a very good function, the crosstalk compensation. So, what can we do with the crosstalk compensation? So we have here the example on the left side without CTC, and on the right side with CTC. So we do a 5 mm circular stud, and the first 5 mm are with a feed rate of 5000 mm per minute, and the second 5 mm are with 16,100 mm per minute. So you see the cutting time. The first 5 mm are cutted in 196 seconds, and the second 5 mm are cutted with 64 seconds. And the difference there in the accuracy you can also see here. So in the first 5 mm we have 0.7 micro roundness and 6 micrometers radius deviation. That's okay. But if we make the feed rate higher, then you see we have a really big deviation. If we do the same with CTC active on the right side, then we have the radius deviation is the same like without CTC with 5000, and the roundness deviation is also in tolerance, but we have a better cutting time because the cutting time from before, you can see here, was 64 seconds. So we are in tolerance with the higher cutting time, and that's the advantage of the CTC. So we have we know the behavior of the tool center point better during high feed rate movements, and because of this we get a more accurate result than without CTC. Of course, the most accurate machining result we get with 5000 millimeters feed rate and the CTC on, but the customer will not pay for as accurate as possible. The customer always pays for the tolerance. The workpiece must be in tolerance. We don't get more money if the workpiece is more accurate than tolerance. So we always get the money for intolerance. So for this it's better when we have a faster cutting time. Okay, that's all from my side. I hope you could enjoy this webinar. If you have questions, don't hesitate to contact us. You see the email address and the telephone number. It's our NC programming support. So if you have questions, just call us and we help you. Thank you very much and bye-bye.